everyone, so in this video we are talking about something called exponential functions. In algebra we have three main function families that we're going to talk about this year: linear, quadratic, which we've already covered, and then exponentials. If you've ever heard the term like exponential growth or growing exponentially, that's what we're about to talk about. An exponential function is basically just any time you have a function where the variable itself is an exponent. So something like 2 to the x, 3 to the x, 10 to the x, those are all exponential functions if we put like f of x in front, or the y in front. And then you might have some other stuff, but if you have a variable as an exponent, so the variable itself is an exponent. That's different from linear functions, which just have like the variable with no exponent at all. And then it's different from quadratics, which have a 2 as an exponent, but they don't have the variable itself as an exponent. These are all exponentials. They might get a little crazier. For example, you might have like 2 to the x plus 5, or x minus 1, or you might multiply by like a half in front. But you still have a variable as an exponent. This is still an exponential. These are not. Okay, so before you watch this video, you should go watch the other video I've linked on Google Classroom, which is this video about zombies and exponential growth. So it's by Mashup Math. Go watch that video first. Basically what you learn in that video is, and you should take notes as you watch it, but here's kind of the general formula of any exponential. Whatever this number is that's attached to the x, we call that the base, just represented by letter b. If there's ever a number multiplied in the front, we call that a, just kind of as the leading coefficient. And then there might be some other stuff in there too, but this is kind of the basic form of any exponential equation. When we have growth, exponential growth, our graph looks like this. When we have exponential decay, the graph looks like this. It's decaying, it's decreasing, whereas growth is increasing. Decay just means like it's decreasing at an exponential rate. You also saw in the video the graph of 2 to the x, which was that zombie equation. We're going to actually do that real quick with a piece of paper. So imagine you take a piece of paper. Currently, I have made 0 folds, and I have 1 piece of paper. So this is the number of folds, and this is the amount of like rectangles that I have. Okay, so if I were to fold the paper 1 time, fold in half, I now have 2 rectangles. You can see that. So I folded it 1 time, and now I have 2 rectangles. If I were to fold it again, now I have 4 rectangles if you were to unfold it. So on the second fold, I have 4 rectangles. On the third fold, I would now have 8. You're probably noticing this pattern, which is actually the exact same as that zombie pattern, where it's doubling each time. It's times 2, times 2, times 2. This is at the heart of what an exponential function is. An exponential function is where you multiply by the same number each time. So with linear functions, you're adding a constant number each time, that's the slope. With exponential functions, you're multiplying by the same number each time. And since you're multiplying, it gets bigger and bigger and bigger at a more and more rapid pace. Let's actually graph this really quick. So we've got the point 0, 1, 1, 2, and then 2, 4, and then 3, 8. So you can see how it gets steeper as we go, and it's actually going to get steeper and steeper and steeper. It's going to continue forever, but it does get very steep. However, in this direction, the graph does keep going, but it never crosses the x-axis. It doesn't get flat, it keeps getting smaller and smaller and smaller forever, but it will never cross the x-axis. We do a little dashed line there to show that it's not actually part of the graph. This is what we call an asymptote. And it's just a line that the graph approaches but never crosses. And so there's an asymptote currently right there at 0. It can move. Okay. So this is the graph of 2 to the x, but there are other exponential functions like, let me show you. So here's 2 to the x. You'll notice if I plug in a 1, I get out a 2 because 2 to the first power, if I plug in a 1, is 2. What if I have 3 to the x, or 4 to the x, or 5 to the x, or even 10 to the x? You'll notice the bigger that base is, the steeper it gets. Because if I have 3 to the x and I plug in a 1, I'm going to get out 3. Or if I have 4 to the x and I plug in a 1, I'm going to get out 4. So it just gets steeper and steeper the bigger that base is. And that makes sense because rather than doubling, it's multiplying by 10 each time, or 5. Okay. I also wanted to mention, with a line, the rate of change is the same, no matter where you are on the line. With an exponential, the rate of change changes based on where you're at. For example, right here, the average rate of change is very small, whereas if I look over here, the average rate of change is very big, it's very steep. For example, let's look at the interval 1, 3 versus 4 to 6. On the interval from 1 to 3, it goes up 1, 2, 3, 4, 5, 6 over 2. So the average rate of change here is 6 halves, or 3. But if I looked at the interval 4, 6, 4, we would double again and get 16. 5, we would double again and get 32. 6, we would double again and get 64. If I'm looking at the rate of change on this interval, it is very steep. It's 64 minus 16 over 6 minus 4, which is 2. So what is that, 56? Sorry, 48. And so that is 24. Notice how 24 is a much steeper slope, basically, than this 3 is. So the farther you go, the steeper it gets. Okay, couple asymptote jokes. Here's an asymptote. Further on in your math career, you'll see asymptotes that are vertical. Right now we just have horizontal ones, but here's a little asymptote. Or here's this one. Okay, those are bad. Anyway, again, just to compare exponential versus linear, with exponential, you take an initial value and you multiply by the same thing over and over. The pattern we keep seeing is you start with the initial value of 1, and then you multiply by a 2 over and over again. But it doesn't have to start with a 1. Like, say you start with 5 zombies, and then you double them each time. Or say you start with $1,000 in a bank account, and then you increase it by 2%. It would look like this over and over again. Or linear, it's different. Linear, you start with an initial amount, like 5, and you add the same number each time. So like you would add 2, and then add 2 again, and then you add 2 again. So that's the difference. With linear, it's a constant addition rate. With exponential, you're multiplying, so it gets steeper and steeper. All right. So you're more than welcome to put these in your calculator or Desmos to graph them, but you can also just graph them by hand. which we're just going to do one little example really quick. First of all, for this example, I want to evaluate this function at these three values. That just means like plug it in for x. So if I want to evaluate where it's at -3, let's make a table of inputs and outputs. If I put in -3, I'm going to do 2 times 3, and then put in -3 for x plus 1. You can just do that in your calculator, but basically, you gotta follow order of operations. This is kind of in parentheses, it comes first, exponents here, I guess technically, so 2 times 3 to the -2. And then again, exponents comes before multiplication. So you would do to the power of -2 first, then times 2. You can't multiply these first, you gotta do exponents first. 3 to the -2 is actually the same as 1/3 squared. Remember, a negative exponent becomes positive if you just flip what side of the fraction it's on, and we'll leave the 2 in front. So you can just do this in your calculator if you want, but basically 3 squared is 9, there's a 2 on the top, so it's, 2 9ths. All right, let's plug in 0 and see what happens. So 2 times 3 to the 0 plus 1, just put in 0 for x. And so again, you gotta do the exponents first. So 2 times 3 to the first power. 3 to the first power is just 3, and 3 times 2 is 6. So when I put in 0, I got out 6. Let's put in 1. One plus 1 is 2, so this is 3 squared, which is 9, and then times 2, which is 18. So this actually gives me a pretty decent graph if I just graph these points. The inputs and outputs, remember, correspond to the x and y's on your graph. So I have the point 1, 18, so 1, let's go by 5s, 5, 10, 15. So I've got the point 1, 18, somewhere around here. I've got the point 0, 6, and I've got the point -3, and then 2 9ths is somewhere in here. So you'll notice it makes this exponential shape, just like this. Again, that might be a little off, but at least I have a general idea of what it looks like, and you could always just graph this in your calculator as well. All right, so go ahead and pause the video and try these on your own. This is the practice for today. Just graph them in Desmos, that's fine. But then also evaluate each one at these 3 values, just to kind of make sure you're familiar with how to plug stuff into these functions. So hopefully you've tried those. We're gonna go ahead and just wrap this up. Just to summarize, exponential functions look something like this. They have a variable as an exponent. There are lots of parent functions. Like with quadratics, you only have one parent function, it's just x squared. But with exponentials, any base could be a parent function. Typically you see these two. 2 to the x and 10 to the x are very common ones for exponentials. I think that's it. One final thing I want to say is a few real-world scenarios that have to do with exponential functions would be accumulating debt or interest on a bank account, a lot of money stuff, social media, anytime something goes viral, it happens at an exponential rate, or even, unfortunately, the COVID cases currently looks fairly exponential. If you look at some of the most recent data, this is the entire United States. It's currently doing this kind of shape, which is not what we want when we're talking about pandemics. This is not linear, it's increasing at a more and more rapid rate, and that is not a good thing. Also, you need to know what the graphs of these look like. Keep in mind, typically when we have a parent graph like x squared, it always starts at 0, 0. That is actually not the case with exponentials. they always start at the point 0, 1. That's because if you plug in 0, 2 to the 0 is 1, or 10 to the 0 is 1. So these always start at the point 0, 1, and then increase from there with an asymptote at the x-axis. Keep in mind 10 to the x is going to be steeper than 2 to the x, because if I plug in a 1, like this one's only doubling each time, whereas this one's multiplying by 10 each time. And that's it.